Core pressure is nominal. Altitude 100,000 feet. Engines remain nominal. Attitude nominal. Power is nominal. Approaching MECO. Core pressure is nominal.
Kyle, we're coming up on main engine cutoff.
Yep. Attitude nominal.
That should come about 3 minutes, 50 seconds or so into flight.
PVCs are nominal. Altitude 100.
Stage 1, throttle down.
2 minutes to MECO. Core pressure is nominal. Attitude nominal. Power is nominal. PVCs are nominal. Engines are nominal. DNO 4, 5, and 6 are on. Core pressures remain nominal. Attitude nominal. PVC nominal.
Standing by for engine throttle down.
Altitude 250,000 feet. Core pressure is nominal. Engines remain at 100% and nominal T plus 3 minutes, 30 seconds. Throttle down has begun.
Traveling about 7,200 miles per hour now.
PVC is skewing out in preparation for the MECO event.
Standing by for stage 1 MECO and separation.
MECO. ESS is disabled. We have stage 1 separation. Lower ACS is enabled. Closed loop guidance is enabled.
4 minutes, 20 seconds into the flight. All, as you hear, going very smoothly.
327 second sequencer time.
Kyle, the next mark event will be fairing separation.
Antares is now in a coast phase until proper conditions for fairing separation and stage 2 ignition are achieved. Power is nominal. Attitude nominal. Power nominal.
That's a view inside the fairing, right? Yeah.
That's correct. View looking forward now.
Power is nominal. Awaiting fairing separation in preparation for interstage separation and then stage 2 ignition. All systems remain nominal at this time. Avionics power is nominal. Fairing separation. Interstage separation. Attitude nominal.
Standing by for stage 2 ignition.
Stage 2 ignition. Attitude nominal.
Stage 2 ignition comes at an altitude of 117 miles.
Power is nominal.
Traveling 9,400 miles per hour.
PVC nominal. Attitude remains nominal.
So Kyle, now we see an animated view of the vehicle, the second stage.
Avionics power nominal.
As reported, burning nominally.
Attitude nominal.
And
looks like stage 2 burns for about 2.5 minutes.
That's correct.
PVC nominal. Attitude nominal. Power is nominal. PVC remains nominal. Attitude nominal.
Well, this is an animated sequence. We are receiving direct telemetry from the vehicle
Power is nominal.
that corresponds to this animation.
Attitude nominal and PVC steering is nominal. Avionics power is nominal. Attitude nominal, still good, strong telemetry here in the RCC. Motor pressures look nominal.
We have about 1 minute remaining before stage 2 tail off begins, and the stage 2 coast phase begins just a little bit after 8 minutes into the flight. We're currently at 7 minutes, 10 seconds.
Attitude is nominal.
Kyle, there you see a great shot of the second stage powered flight.
Score is nominal. Attitude nominal. Power is nominal. PVC nominal. Attitude nominal.
And we're standing by for stage 2 tail off.
20 seconds till burnout. Attitude is nominal. Motor pressures look good. PVC performance is nominal.
Speed is now 16,600 miles per hour.
Attitude nominal. T plus 8 minutes. Power is nominal. Attitude nominal. PVC is nominal. H2 tail off. H2 burnout, FTS disabled. Antares performance is nominal. First P-pod separation. Antares is in orbit. Attitude nominal. Antares will coast for roughly 100 seconds to allow residual thrust tail off prior to the test mission payload separation. Power is nominal. Attitude remains nominal.
So Kyle, now we're in an unpowered coast until we come up to the
Second P-pod separation.
mass simulator separation. As you hear
Attitude nominal.
being called, we're also deploying the secondary payloads that we discussed
P-pod
earlier.
9 minutes.
Everything's going very smoothly. That
1
Cygnus,
minute
or
payload.
the mass simulator
Attitude
separation comes about 10 minutes, just about 1 minute from now.
Attitude remains nominal. Power remains nominal. All systems for Antares remain nominal as we await payload separation. T plus 9 minutes, 30 seconds. 30 seconds to payload separation.
That mass simulator separation is going to occur at an altitude of 158 statute miles, about 255 kilometers.
Attitude nominal.
About 15 seconds from separation.
Power is nominal. Attitude nominal. T plus 10 minutes. Payload separation.
Kyle, as you can see on the animation, the payload has separated successfully.
It's a beautiful, beautiful mission, and it's
There's
got just a few more minutes to go.
Initiated and attitude is nominal. Antares has delivered the A1 test mission payload into orbit.
you see congratulations all around in the Range Operations Center there. And as you mentioned, the mission itself has about 8 more missions as we execute a collision avoidance maneuver on the upper stage with the attitude control system.
And you'll see the
The fact that 2012, the date in 2012 is close to 2014 is completely a coincidence. This up-and-coming solar cycle, roughly 2014, is not really going to be significantly different than the next one, then the next one, and then the previous one. The sun is what we call an active star, and it has a cycle of activity. Over 11 years, we go to higher activity and back down to lower activity. And so this 11 years is fairly steady, and it's been happening through time as far as we can tell. And we always have solar flares. Sometimes we have big ones, sometimes we have small ones. We live on a planet with a very thick atmosphere. And so that atmosphere stops all of the harmful radiation that is produced in a solar flare. Even in the largest events that we've seen over the past 10,000 years, we see that the effect is not enough to damage the atmosphere such that we are no longer protected. Coronal mass ejections are happening on the sun all the time, and they hit the Earth once or twice a week, sometimes more. And in general, the effects are minimal. If we have a really big one, you can have a very strong aurora, but then it can affect satellites and power grids. And so these are the kind of things that people who run these systems know about. And we have warning. These CMEs travel at speeds that mean that they take probably 2 to 3 days to get here. We've learned more and more about storms. We've learned how to better predict the effects, where they're going to go, where they're going to hit. As long as we continue paying attention to it and learning more about it and treating it like we treat a hurricane coming or a huge thunderstorm coming, we can take appropriate measures to prepare for them. We understand the sun well enough with all of the technology and all the science and all of the many spacecraft that we have that are monitoring it 24 hours a day, 7 days a week, to know that this superstorm that's going to wipe out the Earth simply isn't going to happen.
How do you land on Mars? Very carefully. Your spacecraft hurtles toward the planet at thousands of miles per hour, so you'll have to hit the brakes in a hurry. First, your capsule needs a heat shield. It protects the spacecraft inside from the heat and friction of entry into the atmosphere. Friction slows you down over 90%, but not enough to land safely. Use a parachute to slow down even more. Still, falling at over 100 miles per hour, you need the right system to land safely. Here are some options. With a small to mid-size rover, use a cushion of airbags along with retro rockets. Impact at 30 miles an hour and bounce to a stop. With a large lander, use retro rockets and landing legs to touch down going about 6 miles an hour. Or with a large heavy rover, use a big jetpack to slow down to under 2 miles an hour. Then gently lower it on cables to land on its wheels. Any way you do it, you'll need skill and hard work. There's nothing easy about landing on Mars.
Less than 30 seconds now until launch. The auto sequence has started, and the ground umbilical for the third stage and tower have separated. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There you see Progress 51 lifting off at 5:12 a.m. Central Time from the Baikonur Cosmodrome in Kazakhstan. Everything going as planned. 40 seconds into today's launch. Soyuz has 3 stages. The first has 4 liquid engines strapped to the side of the core vehicle, and each of those will burn for about 1 minute and 58 seconds before they're jettisoned. Everything continuing to look good as the Progress 51 makes its way toward orbit.
Hi, I'm Joel Hurwitz, a scientist with Curiosity's Surface Sampling System team, and this is your Curiosity Rover Report. This week, the Curiosity science team released its initial findings from its first ever drilled sample on Mars. This sample was collected from the John Klein drill site, which is located about 500 meters east of where we landed about 7 months ago. Curiosity obtained her first drill sample and passed that sample on to her onboard analytical instruments called ChemIn and SAM. These powerful instruments tell us about what minerals are present in these rocks and whether they contain the ingredients necessary to sustain life as we know it. What the Curiosity team has found is incredibly exciting. When we combine what we've learned from our remote sensing and contact science instruments with the data that's coming in from ChemIn and SAM, we get a picture of an ancient, watery environment which would have been habitable had life been present in it. As an example, the information that we're getting from the ChemIn instrument tells us that the minerals that are present in this lakebed sedimentary rock at John Klein are very different from just about anything we've ever analyzed before on Mars, and they tell us that the John Klein rock was deposited in a freshwater environment. This is an important contrast with other sedimentary environments that we've visited on Mars, like the Meridiani Planum landing site, where the Mars Exploration Rover Opportunity has been operating since 2004. At that site, sedimentary rocks record evidence of an environment that was only wet on a very intermittent basis. And when it was, the waters that were there were highly acidic, very salty, and not favorable for the survival of organic compounds. This is in direct contrast to the freshwater environment we're seeing here at the John Klein site. The SAM instrument is telling us that these rocks contained all the ingredients necessary for a habitable environment. We found carbon, sulfur, and oxygen, all present in a variety of states that life could have taken advantage of. All in all, these few tablespoons of powder from a Martian rock have provided the Curiosity science team with an exciting new data set that tells us that Gale Crater, and perhaps all of Mars, contained habitable environments. This is an incredible success for the Curiosity mission to Gale, and the science team is looking forward to digging deeper into Mars's ancient watery past in the weeks, months, and years ahead. This has been your Curiosity Rover Report. Check back for more updates.
I'm Ashwin Vasavada, the Mars Science Laboratory Deputy Project Scientist, and this is your Curiosity Rover Report. Curiosity has been continuing the analysis of the John Klein area, where it drilled into rock and acquired its first sample of rock powder. After delivering a number of small portions to SAM and ChemIn, Curiosity dumped the remaining material in two piles. One pile is made up of material that went through a sieve, the rest wasn't sieved. We put those piles near the original holes so that instruments on Curiosity's arm and mast, like ChemCam, could study them all together. Curiosity's science team reported their progress in unraveling the different chemical compositions of rocks, soil, and dust. The ChemCam team fired a series of laser shots right down the side of the drill hole, revealing how composition changes with depth. In spite of all the busy work on the rocks and dust, Curiosity occasionally does take time to stop and smell the atmosphere. The SAM instrument took a deep breath last week in order to look at a gas called argon. SAM compared the amount of light argon, argon-36, and a heavier form, argon-38. SAM found that the mix of argon at Mars today is heavier than in the Earth's atmosphere, the Sun, and in Jupiter. These measurements are evidence that Mars once had a thicker atmosphere, and much of it was lost long ago. That would help explain the evidence for rivers and lakes in the past, in spite of the cold and dry conditions today. Through the month of April, Mars will be behind the Sun as seen from Earth. This planetary alignment, called solar conjunction, happens every 26 months. Because the Sun can disrupt radio signals between Curiosity and Earth, we won't send any more commands to Curiosity until we know that they'll be safely received. In the meantime, the operations team will listen for a daily signal from the rover, letting us know that it's healthy and continuing to study the weather and space radiation all on its own. We'll plan to pick up science operations once again in early May. This has been your Curiosity Rover Report. Please check back for more updates.
Three, two, one. Relay, motion. engaging. Flash engaged. Yep. Sequence is still running. Just going to drive arm move back. Right back.
One, zero, and liftoff.
We have spacecraft separation and confirmation from our video system.
Approximately 50 minutes after launch, the spacecraft separates from the upper stage of the launch vehicle. 6 minutes after that, the spacecraft transmitter sends a signal back to Earth, which is received by the tracking stations. Once we receive that signal, we're ready to send our first command up to the spacecraft, and that actually marks the beginning of the cruise phase.
There are some incredible challenges on the way to Mars. One of the things is there are always anomalies. There are always things that are going to go wrong that you never expected. You have a baby spacecraft that is now on its way to Mars, and it's seeing the space environment for the first time. So it's going to see temperature ranges from minus 250 degrees Fahrenheit to plus 250 degrees Fahrenheit. And you've got instruments all over the spacecraft. You've got propellant lines that you can't let freeze. And so there's always this challenge of keeping the entire spacecraft tuned thermally.
Some of the things that we're going to be doing during the cruise phase are some trajectory correction maneuvers, which are basically pushing us along the path of where we want to end up when we arrive at Mars. The launch vehicle puts us at a specific path on a trajectory, and along the way from here to Mars, over the 9 months that we're going to be flying there, we need to make small corrections to that.
If you were trying to shoot a bow and arrow at a bullseye, at a target, and you had drawn back the bow and you had shot off the arrow, and you realized all of a sudden that it wasn't actually going to hit the target, how great would it be if you could pause in the middle, make a slight adjustment to the arrow,